Introduction to TLS 1.3. Welcome to the channel. Please consider subscribing. I produce videos daily covering a wide variety of cloud topics with focus on networking. Also, hit the bell icon to get notified of new videos. Today we're diving deep into TLS 1.3, the latest version of the transport layer security protocol that secures most of the internet traffic you interact with every single day. Whether you're browsing websites, checking email, or accessing cloud services, TLS is working behind the scenes to protect your data. TLS 1.3 represents a major evolution in internet security. It was officially published in August 2018 after 4 years of development and extensive debate within the IETF community. This wasn't just a minor update, it was a complete rethinking of how we establish secure connections. The driving forces behind TLS 1.3 were speed and security. The internet had changed dramatically since TLS 1.2 was released in 2008. Mobile devices became dominant, users expected instant page loads, and attackers had become far more sophisticated. The old protocol needed modernization. In this presentation, we'll explore how TLS 1.3 works from the ground up. We'll examine the handshake process, understand the cryptographic improvements, and see why major companies like Cloudflare, Google, and Facebook pushed so hard for its adoption. By the end, you'll understand not just what TLS 1.3 does, but why it does it that way. What is TLS? Before we dive into TLS 1.3 specifically, let's establish what TLS actually is and why it matters. TLS stands for Transport Layer Security, and it's the cryptographic protocol that provides secure communication over a computer network. You probably know its predecessor better, Secure Sockets Layer, or Secure Sockets Layer. When you see that little padlock icon in your browser's address bar, that means TLS is active. Every time you visit a website with HTTPS instead of HTTP, TLS is encrypting all the data traveling between your browser and that server. Without it, anyone between you and the server could read your passwords, credit card numbers, personal messages, everything. TLS provides 3 critical security properties. First is confidentiality through encryption. This means nobody can read your data in transit. Second is integrity through message authentication codes. This means nobody can modify your data without detection. Third is authenticity through certificates. This ensures you know you are actually talking to the real server and not an imposter. The protocol operates at the transport layer, sitting between your application protocols like HTTP and the underlying TCP connection. This positioning makes it incredibly versatile. TLS can secure web traffic, email, instant messaging, VPNs, and countless other protocols. It has become the universal security layer for the internet. TLS evolved from SSL, which was originally developed by Netscape in the 1990s. SSL 3.0 became TLS 1.0 in 1999 when the IETF took over its development. We have since had TLS 1.1, 1.2, and now 1.3. Each version has added improvements, but TLS 1.3 represents the biggest leap forward yet. Understanding what TLS does sets the foundation for appreciating what makes version 1.3 so special. TLS 1.2 versus TLS 1.3. To truly appreciate TLS 1.3, you need to understand what it improved upon. TLS 1.2 served us well for a decade, but it had accumulated significant baggage over the years. It supported dozens of Cipher suites, many of which were outdated or vulnerable. The handshake required 2 full round trips before any application data could be sent, adding latency to every connection. The TLS 1.2 handshake was also complex and had several security vulnerabilities that were discovered over time. Attacks like Beast, Crime, Breach, and POODLE exploited various weaknesses in the protocol. While these were patched, they revealed fundamental design issues that needed addressing. TLS 1.3 took a clean slate approach. The IETF working group removed everything that wasn't necessary or secure. They eliminated support for older Cipher suites, including RSA key exchange, static Diffie-Hellman, and all Cipher suites without forward secrecy. This dramatically reduced the attack surface. The performance improvements in TLS 1.3 are equally significant. The handshake now requires only one round trip instead of two, cutting connection establishment time in half. For returning visitors, TLS 1.3 introduces zero round trip time resumption, meaning application data can be sent immediately with the first packet. This makes a huge difference for user experience, especially on mobile networks with higher latency. Security was strengthened through mandatory forward secrecy, which means even if a server's private key is compromised in the future, past communications cannot be decrypted. The protocol also encrypts more of the handshake, hiding metadata that could reveal information about the connection. Every design decision in TLS 1.3 prioritizes both security and speed, making no compromises between them. The TLS 1.3 Handshake Overview. The handshake is the heart of TLS. It is where the client and server establish a secure connection before exchanging any sensitive data. In TLS 1.3, this process has been streamlined dramatically, while also becoming more secure. Understanding the handshake is crucial because it happens billions of times each day across the internet. The TLS 1.3 handshake accomplishes several goals in a single round trip. The client and server must agree on a protocol version, select a Cipher suite, authenticate the server, and derive encryption keys. In previous versions, this took multiple back-and-forth exchanges, but TLS 1.3 optimizes this beautifully. A clever technique makes the one-round-trip handshake possible. The client speculatively sends key share information in its very first message. Instead of waiting to see what the server supports, the client makes educated guesses about which key exchange algorithms the server will accept, and includes those key shares immediately. The server receives this initial message. If the client correctly guessed the supported algorithms, the server can immediately generate its response, containing everything needed to establish the encrypted connection. Both sides can then derive the same encryption keys and start sending encrypted application data right away. This optimization matters tremendously for user experience. Every round trip on a network takes time, potentially hundreds of milliseconds on mobile networks or for users far from the server. By eliminating one round trip from the handshake, TLS 1.3 makes every HTTPS connection faster, and this adds up to a noticeably snappier web experience. Pages load faster, API calls return quicker, and users are happier. TLS 1.3 Handshake Flow. Let's walk through the TLS 1.3 handshake step by step so you can see exactly how this elegant process works. This diagram shows the full message flow between a client and server establishing a secure connection. Every arrow represents a message traveling across the network. The handshake begins with the client hello message. This is the client introducing itself and saying what it is capable of. The client includes several critical pieces of information: the TLS versions it supports, the Cipher suites it knows, any extensions it wants to use, and here's the key innovation: key shares for one or more key exchange algorithms. The client is essentially saying, here are my proposed encryption parameters, and here are my public keys for generating the shared secret. The server receives the client hello and must make decisions. It selects the TLS version to use, picks a Cipher suite from those offered by the client, and chooses a key exchange algorithm. The server responds with a server hello message containing its selections, plus its own key share for the chosen algorithm. At this point, both client and server have enough information to derive the shared secret and generate encryption keys. Here's where TLS 1.3 gets really interesting. After the server hello, all remaining handshake messages are encrypted. The server sends its certificate to prove its identity, along with a certificate verify message containing a digital signature that proves the server possesses the private key for that certificate. Finally, the server sends a finished message containing a MAC of the entire handshake transcript. The client verifies the server's certificate, checks the signature, and validates the finished message. If everything checks out, the client sends its own finished message. At this point, the handshake is complete, and both sides can begin sending encrypted application data. Notice that only 2 round trips occurred. Client hello and server hello in the first round trip, then the server's encrypted messages and client's response in the second. This is a massive improvement over TLS 1.2's 3 round trips. Client hello message details. The client hello message is packed with information, so let's break down what's actually being sent in that first packet from client to server. This is where negotiation begins, and every field plays an important role in establishing the secure connection. The supported versions extension tells the server which TLS versions the client can speak. In TLS 1.3 client hello, this will include 1.3 and potentially 1.2 for backward compatibility. The server will pick the highest version both sides support. This is more secure than the old version negotiation method, which was vulnerable to downgrade attacks. The Cipher Suites field lists all the Cipher suites the client supports, in order of preference. A Cipher suite is a bundle that specifies the key exchange algorithm, authentication method, encryption algorithm, and MAC algorithm. TLS 1.3 only supports 5 Cipher suites, all of which provide strong security. The client might list something like TLS AES 256 GCM SHA384 or TLS CHA 20 Poly 1305 SHA256. The KeyShare extension is the game changer. Instead of waiting for the server to say which key exchange algorithm it wants, the client speculatively includes public key shares for one or more algorithms. Typically, the client will include a key share for the most commonly used algorithm, usually X25519, which is an elliptic curve Diffie-Hellman algorithm. This allows the server to immediately compute the shared secret without an extra round trip. Other important extensions include server name for SNI, or server name indication, which tells the server which hostname the client is trying to reach. This is essential for servers hosting multiple websites on the same IP address. The supported groups extension lists which elliptic curves or Diffie-Hellman groups the client supports. The signature algorithms extension specifies which signature schemes the client accepts for certificate validation. All of this information flows in a single UDP or TCP packet, allowing the server to make all its decisions immediately upon receipt. This front-loading of information is what enables the one round-trip handshake that makes TLS 1.3 so fast. Server hello and key exchange. When the server receives the client hello, it springs into action, making critical decisions and preparing its response. The server hello message is the server's reply, and it is where the server commits to specific cryptographic parameters that will be used for this connection. First, the server examines the supported versions extension and selects TLS 1.3 if it supports it. Next, it looks at the Cipher suites list and chooses one Cipher suite that both client and server support. The server will typically pick the strongest Cipher suite that appears in both the client's list and its own preferences. Modern servers often prefer AES GCM or CHA 20 Poly 1305. Now comes the crucial key share decision. The server looks at which key shares the client provided in its client hello. If the client included a key share for an algorithm the server wants to use, that's great. The server can proceed immediately. The server generates its own key pair for that same algorithm, includes its public key in the server hello, and can immediately compute the shared secret using its private key and the client's public key. This shared secret is the foundation of all subsequent encryption. Both the client and server can independently compute the same shared secret without ever transmitting it across the network. This is the magic of Diffie-Hellman key exchange. From this shared secret, both sides derive multiple encryption keys using a key derivation function. Separate keys for client-to-server traffic, server-to-client traffic, and handshake encryption. What happens if the server doesn't like any of the key shares the client provided? The server can send a hello retry request message asking the client to send a key share for a different algorithm. This adds a round trip, but it's rare in practice because clients typically include the most common algorithms. The hello retry request mechanism ensures compatibility while optimizing for the common case. By the time the server hello is sent, encryption keys have been established. Every message after server hello is encrypted, including the server's certificate. This is a significant security improvement over TLS 1.2, where the certificate was sent in plaintext, potentially leaking information about which websites a user is visiting. Server authentication. Authentication is critical. The client needs proof that it is actually communicating with the legitimate server and not an attacker performing a man-in-the-middle attack. In TLS 1.3, server authentication is performed using digital certificates and cryptographic signatures. And importantly, all of this now occurs under encryption. The server sends its certificate in the certificate message. This certificate is an X.509 digital certificate, issued by a Trusted Certificate Authority, or CA. The certificate contains the server's public key, the domain name it is valid for, the CA that issued it, and the CA's digital signature vouching for the certificate's authenticity. Your browser or application maintains a list of trusted CAs and will verify that the certificate chains back to one of these trusted routes. The client performs several validation checks on this certificate. It verifies the certificate hasn't expired, checks that the domain name matches the server name the client intended to connect to, validates the CA's signature on the certificate, and ensures the certificate hasn't been revoked by checking certificate revocation lists or using OCSP, also known as Online Certificate Status Protocol. But simply possessing a valid certificate isn't enough. The server must prove it actually controls the private key associated with that certificate's public key. This is where the certificate verify message comes in. The server creates a digital signature, using its private key, over a hash of the entire handshake transcript up to this point. The client then verifies this signature using the public key from the certificate. This signature proves two things simultaneously. First, the server possesses the private key for the certificate, so it is not just replaying someone else's certificate. Second, the signature covers the handshake transcript, which includes the client's random values and key shares, binding this authentication to this specific connection and preventing replay attacks. TLS 1.3 encrypts the certificate and certificate verify messages, which is a major privacy improvement. Passive network observers cannot see which certificate was presented, making it harder to determine which website you are visiting. This protects user privacy and makes censorship more difficult. Finished messages and handshake completion. The handshake concludes with finished messages exchanged by both parties. These messages serve as the final verification that the handshake completed successfully and that both sides derived the same keys. This is the cryptographic equivalent of both parties confirming that everything looks good on their end, allowing them to proceed. The finished message contains a MAC or message authentication code computed over the entire handshake transcript. This transcript includes every message sent by both client and server from client hello through the message immediately before finished. The MAC is computed using a key derived from the master secret, ensuring only parties with the correct keys can generate valid finished messages. When the server sends its finished message, it is asserting that it has correctly received and processed all your handshake messages, derived these encryption keys, and is ready to proceed. The client verifies this MAC by independently computing what the MAC should be, based on its view of the handshake. If the MACs match, the client knows the server derived the same keys and saw the same handshake messages. The client then sends its own finished message. This message includes a MAC of the complete handshake, which incorporates the server's finished message. The server similarly verifies this MAC only after both finished messages are successfully verified. Do the client and server begin sending application data? This mutual verification ensures that both parties agree on every detail of the handshake before any sensitive data is transmitted. The finished messages also provide protection against truncation attacks where an attacker tries to prematurely terminate the handshake. Since the finished MAC covers all handshake messages, any tampering or missing messages will cause the MAC verification to fail, alerting both parties to the attack. At this point, the TLS 1.3 handshake is complete. The entire process, from client hello to the first application data, happens in just one round trip in the common case. Both parties have authenticated each other, agreed on cryptographic parameters, and established encryption keys. Secure communication can now begin with minimal latency overhead. Zero round-trip time resumption. One of the most impressive features of TLS 1.3 is zero RTT or zero RTT resumption, which allows clients to send encrypted application data in the very first message of a resumed connection. This eliminates all handshake latency for returning visitors, making subsequent connections instantaneous from a TLS perspective. Here's how zero RTT works. When a TLS 1.3 connection is first established, the server can optionally provide the client with a pre-shared key, or PSK, along with a ticket. This ticket is essentially a token that the server will recognize in the future. The client stores this ticket and PSK securely. When the client wants to reconnect to the same server later, maybe the user closes and reopens their app, it can use zero RTT. In the zero RTT scenario, the client includes the ticket in its client hello along with early application data encrypted using keys derived from the PSK. The client does not wait for the server's response. It immediately sends its HTTP request or other application data. This means the application data travels in the very same packets as the client hello, achieving true zero round-trip time. The server receives the client hello, recognizes the ticket, retrieves the associated PSK, and can immediately decrypt and process the early data. The server continues with a regular handshake to establish fresh keys for the ongoing connection, but the critical first request has already been processed without waiting for any round trips. However, zero RTT comes with important security considerations. The early data is not protected against replay attacks. An attacker could capture the zero RTT data and replay it to the server, causing the same request to be processed multiple times. For this reason, zero RTT should only be used for idempotent requests, which are operations that can safely be executed multiple times without causing problems. Reading data is fine, but requests that modify server state should not use zero RTT. Despite the replay risk, zero RTT provides enormous performance benefits for appropriate use cases. Websites can use it for initial page loads, CDNs can accelerate content delivery, and mobile apps can reduce latency for API calls. When used correctly, zero RTT makes secure connections feel instantaneous, eliminating one of the last performance penalties of encryption. Cipher suites in TLS 1.3. TLS 1.3 dramatically simplified Cipher suite selection by supporting only 5 Cipher suites, all of which provide strong security guarantees. This is a massive reduction from TLS 1.2, which supported dozens of Cipher suites, many of which were weak or vulnerable. The simplification reduces implementation complexity and eliminates entire classes of vulnerabilities. Let's look at what's included. TLS AES 128 GCM SHA-256 uses 128-bit AES encryption in Galois/counter mode with SHA-256 for hashing. This is the most common choice, offering excellent performance and strong security. The GCM mode provides both encryption and authentication in a single operation, which is faster than separate encrypt than MAC approaches. TLS AES 256 GCM SHA 384 is similar, but uses 256-bit AES for even stronger encryption and SHA 384 for hashing. This is preferred in high-security environments where the extra security margin justifies the slight performance cost. Government and financial organizations often mandate 256-bit encryption. TLS CHA-20 Poly 1305 SHA 256 is particularly interesting. CHA-20 is a stream cipher designed to be fast in software, especially on devices without hardware AES acceleration, like mobile phones. Poly 1305 provides authentication. This cipher suite performs exceptionally well on ARM processors and is often the best choice for mobile applications. TLS AES 128 CCM SHA 256 and TLS AES 128 CCM 8 SHA 256 use AES in counter with CBCM-AC mode. CCM is designed for constrained environments like Internet of Things devices where memory and processing power are limited. The CCM-8 variant uses a shorter authentication tag to save bandwidth, though this provides slightly lower security margins. Notice what's missing from TLS 1.3. No RSA key exchange, no CBC mode ciphers, no RC4, number 3 DES, no MD5, no SHA1. All of these have known weaknesses or have been broken. By eliminating them entirely, TLS 1.3 forces everyone to use modern, secure cryptography. There's no option to negotiate down to a weak cipher suite, which was a major source of vulnerabilities in older TLS versions. Every TLS 1.3 cipher suite provides authenticated encryption with additional data, or AEAD, forward secrecy through ephemeral key exchange, and modern hash functions. This means that, no matter which cipher suite is negotiated, you are getting strong security. The choice between cipher suites becomes more about performance and hardware capabilities than security level. Forward secrecy explained. Forward secrecy, also called perfect forward secrecy or PFS, is one of the most important security properties in TLS 1.3. It ensures that even if a server's long-term private key is compromised in the future, past communications cannot be decrypted. This protects historical data from retroactive surveillance or breaches. To understand why this matters, consider TLS 1.2 with RSA key exchange. In that mode, the client generates a random session key, encrypts it with the server's public RSA key from the certificate, and sends it to the server. The server decrypts it with its private key, and both sides use this session key for the connection. The problem is if an attacker records all this encrypted traffic and later obtains the server's private RSA key, for example, through a server breach, a stolen backup, or legal coercion, they can go back to their recorded traffic, decrypt the session keys, and decrypt all past communications. TLS 1.3 achieves forward secrecy by requiring ephemeral Diffie-Hellman key exchange for every connection. Ephemeral means that the keys are temporary and are generated fresh for each connection. Here's how it works. The client generates a temporary key pair just for this connection, sends the public key to the server, and then immediately discards the private key after deriving the session keys. The server does the same thing with its own temporary key pair. The magic is that the shared secret is computed from these temporary keys and never transmitted across the network. After both sides derive the session keys, they delete the temporary private keys. Even if an attacker records the entire handshake, they only see the public keys, which aren't sufficient to compute the shared secret. You need at least one private key for that, and both private keys have been deleted. If the server's certificate private key is later compromised, the attacker gains nothing for past connections. They could potentially impersonate the server in new connections, but they cannot decrypt old recorded traffic because those connections used different ephemeral keys that no longer exist. Each connection's secrets died with that connection. This is incredibly important for long-term privacy, Organizations might keep encrypted traffic logs for years. With forward secrecy, a future breach doesn't expose all that historical data. Whistleblowers, journalists, and everyday users are all protected by forward secrecy. It's a powerful defense against both targeted attacks and mass surveillance programs that collect encrypted traffic hoping to decrypt it later. Encrypted handshake. One of the most significant security improvements in TLS 1.3 is that most of the handshake is encrypted. In TLS 1.2, the handshake was largely sent in plaintext, which leaked substantial information about the connection. TLS 1.3 encrypts everything after the server hello, providing much better privacy and security. Let's understand what was visible in TLS 1.2. An observer could see the server's certificate in plaintext, which reveals exactly which website you are connecting to. They could see all the extensions being negotiated, the Cipher suites considered, and various other metadata about the connection. This information enabled surveillance, censorship, and targeted attacks. Governments could easily block access to specific websites just by inspecting TLS handshakes. TLS 1.3 changes this dramatically. After the initial client hello and server hello, which must be in plaintext for bootstrapping purposes, everything else is encrypted. The server certificate, certificate verification, extensions, and all other handshake messages are protected. An observer can only see that a TLS connection is being established, but not to which specific server or with what parameters. The encryption happens immediately after key derivation. Once both client and server compute the shared secret from the key exchange, they derive handshake traffic keys and begin encrypting. The certificate message, certificate verify, and even extension data all flow encrypted. This protects the server's identity, making traffic analysis much harder. However, there is a remaining privacy leak, the server name indication or SNI extension in the client hello. SNI is used to tell the server which hostname you are connecting to, necessary when multiple websites share an IP address. Unfortunately, SNI must be sent before encryption is established, so it remains visible in plaintext. This means observers can still see which hostname you are trying to reach. The TLS working group recognized this issue and developed encrypted client hello or ECH, previously called ESNI. This extension encrypts the SNI and other client hello data, closing the remaining privacy gap. ECH is being deployed gradually across the Internet. When fully adopted, TLS 1.3 with ECH will provide end-to-end encryption of handshakes, revealing minimal information to network observers. The encrypted handshake makes censorship much harder, improves user privacy, and reduces the attack surface by hiding configuration details from potential attackers. It is a major step forward in making Internet communications truly private. Key derivation process. Key derivation is the process of generating multiple cryptographic keys from the shared secret established during the handshake. TLS 1.3 needs several different keys for different purposes, and the derivation process must ensure these keys are cryptographically independent and secure. Let's walk through how this works. The process starts with the shared secret computed from the Diffie-Hellman key exchange. This shared secret is combined with random values from both the client hello and server hello using a key derivation function called HKDF, which stands for HMAC-based key derivation function. HKDF is designed to extract strong cryptographic keys from potentially imperfect random sources. First, an early secret is derived using HKDF extract with the shared secret. From this early secret, the handshake secret is derived. The handshake secret is used to generate 4 separate keys: a client handshake traffic encryption key, a server handshake traffic encryption key, a client handshake traffic MAC key, and a server handshake traffic MAC key. Wait, I misspoke. TLS 1.3 uses AEAD ciphers, so encryption and authentication happen together. The keys are simpler than that. Let me correct that. From the handshake secret, Separate handshake traffic keys are derived for client-to-server traffic and server-to-client traffic. These keys encrypt all handshake messages after the server hello. Having separate keys for each direction prevents various reflection and replay attacks. After the handshake completes, the master secret is derived. From the master secret, application traffic keys are generated. Again, separate keys for client-to-server and server-to-client traffic. These application data keys are what encrypt all your actual application traffic, like HTTPS requests and responses. TLS 1.3 also supports key updates, allowing the connection to generate new encryption keys periodically without performing a new handshake. This limits the amount of data encrypted with any single key, which is a security best practice. If one key is somehow compromised, only the data encrypted with that specific key is at risk. The entire derivation process is designed to ensure that even if one key is compromised, the other keys remain secure. The keys cannot be used to derive each other or to recover the master secret. This compartmentalization provides defense in depth, limiting the damage from any potential key compromise. Session resumption. Session resumption allows a client to reconnect to a server without performing a full handshake, speeding up subsequent connections. TLS 1.3 improved resumption significantly, making it both faster and more secure than in previous versions. Let's explore how the session resumption mechanism works. During an initial TLS 1.3 handshake, the server can send a new session ticket message to the client after the handshake completes. This ticket contains encrypted state information that the server can use to resume the session later. The ticket might include the Cipher suite used, the connection time, and a pre-shared key or PSK derived from the original master secret. The server encrypts the ticket using a key known only to itself, often called the Session Ticket Encryption Key or STEK. This allows stateless resumption, which means the server doesn't need to maintain a database of active sessions. All the session state is stored in the ticket itself, which the client keeps. This is a huge scalability win for large server deployments. When the client wants to resume the connection, it includes the session ticket in the pre-shared key extension of its client hello. The server decrypts the ticket, verifies it is still valid, and if so, uses the PSK from the ticket instead of performing a full Diffie-Hellman exchange. The handshake still happens, but it is abbreviated. No certificate exchange is needed because the server was already authenticated in the original connection. Importantly, TLS 1.3 resumption can still include ephemeral Diffie-Hellman even with PSK, providing forward secrecy. This mode is called PSK with DHE, and it's the recommended approach. The PSK proves the client previously connected, but fresh ephemeral keys ensure that compromising the PSK later doesn't reveal traffic from the resumed session. Session tickets can have expiration times, limiting how long they are valid. Servers often rotate their ticket encryption keys regularly, which automatically invalidates older tickets. This balances the performance benefits of resumption with security concerns about long-lived credentials. The resumption handshake is faster than a full handshake because certificate validation can be skipped. However, it is not as fast as 0RTT, which we discussed earlier. Resumption still requires one round trip, while 0RTT eliminates even that. Many deployments use both, regular resumption for stateful requests and 0RTT for safe idempotent requests. Middlebox compatibility. One of the biggest challenges in deploying TLS 1.3 was dealing with middleboxes, network devices like firewalls, intrusion detection systems, and proxies that inspect or modify traffic. Many middleboxes were designed with TLS 1.2 in mind and would break or block TLS 1.3 connections. This required clever engineering to maintain compatibility. The core problem is that middleboxes often perform deep packet inspection, examining the contents of TLS handshakes. They expect to see certain patterns that were true for TLS 1.2 but changed in TLS 1.3. For example, Middleboxes might expect to see the server's certificate in plaintext, or might require specific handshake patterns. When TLS 1.3 encrypted more of the handshake and changed message ordering, some middleboxes would treat this as suspicious and drop the connection. To address this, TLS 1.3 includes several compatibility features that make the protocol look more like TLS 1.2 to middleboxes, while still providing all the security improvements. This is often called Middlebox compatibility mode. The changes are purely cosmetic and do not affect security, but they help TLS 1.3 pass through more networks successfully. One major compatibility feature is the change Cipher spec message. In TLS 1.2, this was a meaningful message that signaled the transition to encrypted communication. In TLS 1.3, it serves no cryptographic purpose, but sending it helps middleboxes recognize the handshake pattern. It is essentially a dummy message included just for compatibility. Another compatibility trick involves the session ID field in the client hello and server hello. TLS 1.3 does not actually use session IDs for resumption. It uses PSK tickets instead. However, including a fake session ID in the handshake makes middleboxes think this is a resumed TLS 1.2 session, which they are more likely to allow through unchange. The working group also had to carefully consider version negotiation. A TLS 1.3 client hello advertises itself as TLS 1.2 in the legacy version field, but it includes a supported _versions extension, indicating TLS 1.3 support. Servers that understand TLS 1.3 look at this extension, while older servers and middleboxes only see TLS 1.2 in the legacy field. This prevents middleboxes from blocking connections they do not recognize. These compatibility measures were controversial. Some felt they compromised the clean design of TLS 1.3 just to work around broken middleboxes. Others argued they were pragmatic and necessary for deployment. Ultimately, the compatibility features worked. TLS 1.3 deployment succeeded where previous protocol upgrades had stalled. Today, TLS 1.3 works on most networks, though some enterprise environments still have issues with particularly aggressive inspection appliances. Security Improvements Summary. Let's consolidate all the security improvements in TLS 1.3 because they represent a major advancement in Internet security. Each improvement addresses specific vulnerabilities or attack vectors that affected earlier TLS versions. First, mandatory forward secrecy means all connections use ephemeral key exchange. There's no option to fall back to static RSA key exchange like in TLS 1.2. This protects past communications from future key compromises, defending against retroactive decryption attacks and mass surveillance. Second, the removal of weak Cipher suites eliminates entire classes of attacks. No more CBC mode vulnerabilities like Beast and Lucky 13. No more RC4 biases. No more export-grade cryptography. No more SHA-1 collisions. Every TLS 1.3 Cipher suite provides strong encryption, authentication, and integrity protection with modern algorithms. Third, the encrypted handshake hides most connection metadata from passive observers. Certificate information, extensions, and negotiated parameters are all encrypted. This prevents traffic analysis, makes targeted censorship harder, and protects user privacy. Combined with future encrypted client hello deployment, TLS 1.3 will hide nearly all handshake information. Fourth, improved downgrade protection prevents attackers from forcing connections to use older, vulnerable protocol versions. The finished message MAC covers a hash of the handshake transcript including version information, so tampering with version negotiation will be detected and cause the connection to fail. Fifth, a simplified protocol state machine reduces implementation complexity. TLS 1.2 had many optional features and edge cases that led to bugs like Heartbleed. The cleaner design of TLS 1.3 is easier to implement correctly and audit for security vulnerabilities. Fewer features mean fewer things that can go wrong. Sixth, better key separation through improved key derivation. Each connection phase uses different keys derived from the master secret. Handshake keys are separate from application keys, and keys for each direction are separate. This compartmentalization limits damage from any single key compromise. The cumulative effect of these improvements is substantial. TLS 1.3 eliminates many known attacks against TLS 1.2, makes new attacks significantly harder, and provides better long-term security guarantees. It represents years of security research distilled into practical protocol design. Performance benefits. Beyond security, TLS 1.3 delivers significant performance improvements that make the web faster for everyone. These optimizations reduce latency, accelerate page loads, and improve user experience, especially on mobile networks where latency is higher. The one round-trip handshake is the most visible improvement. TLS 1.2 required 2 round trips before application data could be sent. One for the client hello and server hello, and another for key exchange and certificate verification. TLS 1.3 completes this in a single round trip by having the client speculatively send key shares up front. On a connection with 50 milliseconds of latency, this saves 100 milliseconds per connection. That might not sound like much, but it adds up across billions of connections daily. Zero RTT resumption takes this even further for returning visitors. Application data can be sent immediately with the client hello, eliminating all TLS handshake latency. For a returning mobile application user on a high latency connection, Zero RTT can make the difference between a snappy experience and a frustrating delay. This is particularly valuable for microservices and API calls where many short connections are established. The simplified Cipher suite negotiation also improves performance. With only 5 Cipher suites to consider, servers make decisions faster and spend less CPU time evaluating options. The AEAD Cipher modes like AES-GCM and CHA-CHA 20 Poly1305 are more efficient than separate encryption and MAC operations, requiring fewer cryptographic operations per packet. Modern Cipher suites take advantage of hardware acceleration. AES-GCM benefits from specialized CPU instructions available in modern processors, achieving throughput measured in gigabytes per second. CHA-CHA 20 Poly1305 is optimized for software implementations on devices without AES acceleration, for example, mobile phones and IoT devices. Both provide excellent performance on their respective platforms. Session resumption and PSK modes reduce server load by avoiding expensive certificate operations and public key cryptography on resumed connections. For high-traffic websites handling millions of TLS connections, this represents significant CPU savings and allows serving more users with the same infrastructure. The performance improvements in TLS 1.3 remove one of the historical arguments against encryption, that it's too slow. Today, TLS 1.3 is fast enough that there's no reason not to encrypt everything. The performance penalty is minimal, and on resumed connections with zero RTT, there's essentially no overhead at all. This has enabled the push toward encrypting the entire web. Deployment and adoption. TLS 1.3 deployment has been remarkably successful compared to previous protocol upgrades. Since its finalization in August 2018, adoption has grown steadily across clients, servers, and major internet platforms. Let's look at how this deployment happened and where we are today. Browser support came quickly. Chrome enabled TLS 1.3 by default in early 2018 during the final draft stage. Firefox followed shortly after. Safari and Edge added support in their 2018 releases. Today, essentially all modern browsers support TLS 1.3, covering over 95% of web users globally. Server software also moved fast. OpenSSL 1.1.1, released in September 2018, was the first production-ready implementation. This immediately enabled TLS 1.3 support in web servers like Apache and Nginx that use OpenSSL commercial load balancers, and TLS termination proxies from vendors like F5 and Citrix added support throughout 2018 and 2019. Major Internet companies were early adopters. Cloudflare enabled TLS 1.3 for all customers in 2018, bringing it to millions of websites. Facebook deployed TLS 1.3 to all their services. Google uses TLS 1.3 across their properties, including Search, Gmail, and YouTube. This meant a huge percentage of Internet traffic quickly moved to TLS 1.3. The Content Delivery Network, or CDN, providers have been crucial for adoption. CDNs like Cloudflare, Akamai, and Fastly handle enormous amounts of traffic. Enabling TLS 1.3 on their networks automatically brought the benefits to all their customers. If your website uses a CDN, you are probably already using TLS 1.3 without even knowing it. Mobile platforms have added support to their networking stacks. Android 10 and later support TLS 1.3. iOS 12.2 enabled TLS 1.3 in 2019. This means mobile apps using system HTTP libraries automatically benefit from TLS 1.3 performance and security improvements. Current adoption statistics are impressive. As of 2024, over 50% of TLS connections on the Internet use TLS 1.3. For major websites and mobile apps, the percentage is even higher, often exceeding 80%. The deployment curve has been much steeper than TLS 1.2 adoption was a decade ago. Some challenges remain. Enterprise networks with deep packet inspection appliances sometimes have issues with TLS 1.3's encrypted handshake. Some legacy systems and embedded devices still only support older TLS versions. But these are increasingly edge cases. The momentum is clearly toward universal TLS 1.3 deployment in the next few years, with TLS 1.2 gradually being phased out. Conclusion. We have covered a lot of ground today exploring TLS 1.3. Let us recap the key takeaways. TLS 1.3 represents the biggest upgrade to Internet security infrastructure in over a decade, delivering both better security and better performance simultaneously. The one round-trip handshake makes connections faster, while the encrypted handshake makes them more private. Mandatory forward secrecy protects historical data from future compromises. The elimination of weak Cipher suites removes entire classes of vulnerabilities. Every design decision in TLS 1.3 was made with both security and performance in mind. Zero RTT resumption provides near-instant connection establishment for returning visitors, making encrypted connections feel as fast as unencrypted ones used to be. The simplified protocol design makes implementations easier to audit and harder to get wrong. The result is a protocol that is both more secure and more usable than its predecessor. The successful deployment of TLS 1.3 demonstrates that it's possible to upgrade fundamental Internet protocols even when billions of devices are involved. The careful compatibility work paid off, allowing TLS 1.3 to deploy widely without breaking existing networks. Today, more than half of Internet TLS connections use TLS 1.3, and that percentage grows every month. Looking ahead, the future of TLS includes finishing the deployment of encrypted client hello to close the remaining privacy gaps, continued optimization of implementations to squeeze out every bit of performance, and ongoing research into post-quantum cryptography to prepare for quantum computers that could break current algorithms. TLS 1.3 is a remarkable achievement in protocol design. It shows how the Internet community can come together to build better, more secure infrastructure that benefits everyone. Whether you're a developer implementing TLS, a network engineer deploying it, or an end user whose data it protects, TLS 1.3 makes the Internet safer and faster for all of us. Thank you for your attendance. Please consider subscribing to the channel.